Yeah, thank you, Kira, for the introduction and for the opportunity to present the chapter. Um, this is a very uh, interesting chapter, and it's close to my area of interest, so I decided to give it a go and have a look at it. Um, it's an interesting chapter in the book as well because it doesn't it tries to be timeless. So um, you wouldn't find lots of code um, with detailed um, steps how to achieve something, but there are lots of tips and lots of uh, common sense how to go about solving things, solving concurrency um, problems in the context of Rust programming. So we're in this chapter we have um, I basically stayed with the structure of the chapter. So I tried following up on a few leads. Some for example, I tried to expand on SIMD and uh, tried hardware locality as well, but um, it it was it turned out to be more difficult than I expected, even in the context of the examples. So instead I just I'm going to present the chapter as it is. So we have uh, like in a good fiction book we have a build up, we have the climax, and we have like the where the um, there is the most development and the like points of interest, and we have the resolution. So there are also um, different viewpoints. So we start. The chapter actually starts with presenting uh, problems with concurrency, and it starts with the trouble with concurrency. And I decided to talk about to start talking about concurrency models because this is just a routine um, knowledge that probably many people have to some extent, even whether we know Rust or we don't know Rust, we still have some understanding of how people write concurrent algorithms. Um, but as for the problems, yes, so Jon also talks about the trouble, what he calls the trouble with concurrency, which is the what things that make writing concurrent programs tricky or difficult, and it gives a few pointers how to solve those problems possibly. Um, and yeah, and he talks about some um, about going deeper into the definitions within the standard library, finding things about how concurrent primitives are being implemented or handled, or what type of hardware dependencies are involved uh, with those primitives. Um, and yeah, uh, in the in summary, Jon gives a few tips about uh, organizing the flow of programming flow of a concurrent. Yeah, yeah. I mean to say, he talks about how to design concurrent programs using Rust. So let's go. Um, uh, so the book aims to be independent of the present moment, so it doesn't root itself in the current state of the standard library or specific uh, external libraries or crates. So it tries to um, um, explain how to add concurrency when if and when someone needs it in standard STD Rust programs. So it doesn't go as far as, for example, it's discuss embedded platforms. So also um, it, uh, it 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 explains how to use concurrency primitives, which are commonly found in the standard library, and it doesn't teach how to implement concurrent data structures, and it doesn't teach how to um, optimize your code, which is a different subject. So, but it gives some tips how to organize your um, uh, development process in such a way that um, it's uh, it's conducive to making your programs more high performant. So, in order to see to get some metrics from the code. Also, yeah, about what is required. Of course, yeah, experience with concurrent Rust at the basic level, basic familiarity with multi-core processor architectures, and understanding of how concurrency is even if not implemented, then applied in within programs on a desktop operating system on common architectures. So we have, according to Jon, there are three flavors of concurrency which are supported within Rust. These are basically we can see it as a 2x2 square. So we have single core, single thread, single core, many threads, and many cores, many threads. And there is a degenerate case when there are many cores and single thread, which is kind of managed by the operating system when it schedules the thread to different CPUs. And Jon calls many core, many thread concurrency through parallelism. So, and this is just from the point of view of the language. There are more flavors of concurrency, of course, if we take other consideration into account. So the operating system does a lot of things for us. So as we know, Rust standard library threads are based on so-called P threads on Linux and Mac OS, and on their analogs on Windows. And there are also operating system processes which are supported by the standard library, and things like, for example, sockets for communicating between those processes. Yeah, about terminology, I would like to just talk about concurrent algorithm. Concurrency as something that where components act together and they agree on something. Just they have a common goal, for example, or they share common knowledge, some common value. And parallelism is in the geometric sense, it's something that runs alongside each other, and it doesn't intersect. So we can think about parallel computations on a CPU or a GPU that are completely independent of each other while they are doing the computation. But at some point they need to converge, and this is where concurrency comes into play. As for support for those these three types of concurrency. So we've already discussed async await in asynchronous programming chapter. For true parallelism, Rust supports only one aspect of concurrency, which is multi-threading, and it provides a way to express it makes it possible to express thread safety by means of special annotations on types which propagate through the type system, and these annotations are sent in sync, and they are just contracts which are not there are no proofs for those contracts. They're just annotations, and they mean that having send and sync means that the type that implements them is thread safe, and it can be shared between threads. And also, it's a concurrency that comes as a standard library option and not a compiler feature, such as on compared to other languages. So it's a bit different. Yeah, so yeah, there is a little bit of further reading. There is an interesting, yeah, of course, there is the Rust book, and where all those things have been introduced. And there is an interesting book by Blandi, Orendorf, and Tyndall called Programming Rust with lots of code examples. And there are examples, for example, such as computing an image in parallel. By just yeah, it's a bit a more visual approach to explaining what parallel libraries do. So yeah, going to the basics, Rust has three concurrency models, which are shared memory concurrency, worker pools, and actors, and they are provided by their respective libraries. There are models that are managed by the operating system, and they are also present in the standard libraries, such as fork join, and they are more like I would say probably, yeah, fork join is just like a different aspect of concurrency, and message passing between OS processes through sockets, which I've mentioned before, and this is not covered in the chapter because it's seems to be a special case of channels, but this is probably OS dependent type of concurrency. Let's talk about the shared memory concurrency. Examples are where state is shared between threads and is guarded by a mutex, or state stored in a special hash map, which implements some locking for concurrent applications, such as dash map, or it can be simply a hash map which is wrapped in a lock. So it can have both data and task parallelism. We can have both data parallelism and task parallelism in shared memory concurrency. The state updates usually are such that we cannot change the order of those updates. So, and this use case is probably the best for shared memory concurrency. Also, when using shared memory concurrency, we have to take into consideration that locking and using mutexes and such comes with their trade-offs, and they must be evaluated. And we'll see a few examples later on. Yeah, it might become more difficult to um, to um, to write to a shared variable, for example. Yeah, a simple example of a mutex, just to be um, for completeness sake. So we have a yeah, we have a few threads which will spawn, and so yeah, we basically in this example we are trying to increment each thread is trying to increment the counter by 1, and it finishes. So in the end, we'll have counter equal the number of the threads, because each thread has applied the +1 function to the counter. And so yeah, this is it. This is how basically fork join parallelism, fork join concurrency is implemented. So we join all the threads, so to speak. That is, we wait until they finish, and um, they don't return any values. So we just um, take the value of the shared variable, and this is the value of the computation. So this is an example of a shared memory concurrency. Example with a concurrent hash map is simple. So it's similar to what we've seen with the mutex, but instead of the mutex, we have a hash map here, and we have um, um, a key pair element where we keep all the results of the computation of each individual thread. So each thread tries to acquire this um, uh, key in order to update it, and this is where locking comes. So the concurrent map will um, basically um, let us implement this algorithm in taking into account all the locking steps in order to make the threads perform a correct operation. So the next model is worker pools, and this is where identical threads receive jobs from a shared job queue. Jobs are executed by each thread independently, and in the end, when the jobs are complete, shared memory is used for collecting those results and for managing the job queue. Threads or elements of the elements of the worker pool still work from other threads that are busy, in the sense that the scheduler can, if a job is scheduled to some element in the worker pool, and this element is still computing something and is busy, the scheduler can reassign the job to an idle element, and then and thus speed up the entire computation. So yeah, and so this is the model which is behind Rayon, Tokyo, and such in the standard in STD Rust, and they don't work in no STD, where people probably implement their own worker pools, or probably there are some other libraries. Yeah, as an example, I have here a parallel matrix multiply. So just um, to be brief, instead of um, say having a for loop for um, for rows and a for loop for columns, we have the outer loop, which is um, which creates those parallel tasks, and they get assigned to different parallel threads. And I have the companion code where I wrote a few benchmarks to find uh, which um, style of concurrency is better, and it was a bit surprising for me to find that naive implementations are often better than sophisticated ones. But this will definitely add introduce a speed up in your algorithm. So if you simply change the into iter into pariter, then you will get a noticeable speed up in the computation. Yeah, and Jon also mentions a type of um, um, worker pool concurrency systems, so-called connection pools, where a connection is managed um, by a set of threads, and they basically store connection state, but they can also reuse the same connection um, for different connecting tasks, but they need to implement some non-trivial logic in order to uh, um, in order not to reuse the state from previous tasks in connections which are assigned to new tasks. So about actor concurrency, the model is such that instead of threads, we are thinking about more high-level constructs, and these are called actors. There is one message queue for each actor, and each actor is assigned to its own topic or job, um, its own job. And examples can be, for example, one actor for a database connection, one actor for managing a file, one actor for a structure that has to be accessed by many threads. For delivering messages, simple, the same message passing concurrency approach is commonly used. And the interesting thing is that we don't need logs in order to manage state, and we in actor-based concurrency we mostly use messaging for passing information around. Yeah, there are, since this is a high-level construct, we can have different implementation strategies for actors. They can be just operating system processes communicating via operating system sockets, or it can be containers or pods communicating via HTTP. Yep. And yeah, there are grades such as Arctics, RT, which are very good for writing actor-based concurrent programs. So yes, I have an example about a ping pong example where messages exchange ping and pong. Well, basically, where threads exchange those ping and pong messages. So this is a definition of a message in Arctics, and it always looks like this. There is an interesting result type, which means that in fact in Arctics there is every message can trigger a response, an acknowledgement, and most often acknowledgement is just basic a basic unit type to signify that it has been received. Yeah, so this is how the message is structured, and when an actor needs to send a message, it calls a special method which is do_send, and that gives the reference of the recipient actor as the argument. So this is an example of a ping actor sending a ping message to a pong actor, which is known, whose address is known to the ping actor. And the receiving the message is implemented as a method of a trait. So it's a trait method. The trait is called a handler, or apparently message handler. So this is the handler of a ping message, and it's implemented for the actor that sends pongs. So this is the actor that is supposed to receive pings. So handle, yeah, basically it takes the message, and it takes some context, which is library specific. And I have the complete example in the companion code. So yeah, yeah, Jon talks about the combined asynchronous and parallel programming approaches, where people use futures for handling I/O tasks, and for using, and they also have parallelism for distributing, say, data parallel computations over the CPUs, and this happens at the same time. And there is a little bit of a remark that Jon makes about how futures need to be approached in a parallel program. The futures need to be sent in order to be sent to threads in the worker pool, if this is managed by Tokyo or Rayon, and those futures which are supposed to be executed on processors in parallel need to be spawned explicitly, by which he means that those executors in Tokyo or Rayon, they don't automatically spawn sub-futures in a bigger future. So those futures need to be taken out, and they have to be spawned. So only the top level matters as far as executors are concerned. So yeah, now some examples about of synchronization primitives, which are also asynchronous. And these synchronization primitives are basically special versions of STD sync logs, so logs or primitives, and they are defined in the respective libraries. So if we use Tokyo futures, we then can use Tokyo mutexes, which provide mutual exclusion for data shared between async tasks, or we can have read-write logs, and they provide asynchronous readers, writers log semaphores that limit the number of concurrent operations. Notifies tasks of an event or barriers, which allow asynchronous tasks to synchronize. And other crates which implement similar primitives are async STD and futures. So now we come to the spooky side of concurrency, which is all the problems that may come. So so suppose we've been to some we've studied concurrency, and we have high confidence in the success of our programming enterprise. So we apply concurrency in some way. We pick a concurrency model. We select a library and we write a program, but then we discover that something is not working quite as we expected. And so here we can, we might want to actually go a little bit deeper and find what's wrong. Jon emphasizes the following problem, which is intrinsic to concurrency, and which is coordinating access to resources. So as we might imagine, to read something is in general quite simple, but to write a value is, on the other hand, difficult, and it can lead to so-called data races, or more broadly, race conditions, where threads compete for a resource to take exclusive control of a resource. This is a classic example. It appears, and the first time I saw it was actually in documentation for an ARM processor, where concurrency, where memory ordering models were introduced, and so we can imagine two threads which try to increment a value by 1. And the question is, what is the value of the variable which was incremented after those events? Interestingly, the result can vary depending on how atomic operations happen to execute. So we break down, or the CPU breaks down this operation into atomic ones. So it needs to to load the value of the variable, then apply the operation, and then to store the value of the variable. And this is basically this is where most of the discussion of correctness ends up. So this is where this is this can be found in most so-called problematic issues with concurrency. So yeah, in this example, just to for completeness sake, we read x in thread 1, say x is 0, and then the thread 2 reads the same variable, and x is still 0. And then both threads actually increment that 0. So in the end, the value which comes from thread 2 gets written, and this is the value 1. So obviously this is not the result that we might have expected, because we might have expected the value 2 most likely. Another issue is performance. Performance might even scale down in some cases, and this is quite common for suboptimally implemented programs to get slower. So it doesn't necessarily it's not necessarily true that the more threads the better. We have to think about how many available cores there are, and if there are too many threads and just not enough cores, then we overload the operating system, and that it will try to find available cores for all those threads, and it will spend time scheduling. And there may be some scheduling issues associated with that, such as priority inversion and such. We've talked about race conditions, and they are related, somewhat related to resource contention, where multiple threads try to say use the same network connection, and they use all the bandwidth, and so there is no bandwidth left for if we are to add more threads. And this can also lead to potential deadlocks. So if there's just not enough of that resource that's required. So yeah, I would add that Jon talks about something that in my mind goes back to the pigeonhole principle. If n pigeons fly into m pigeonholes and n is greater than m, then at least one pigeonhole must contain more than one pigeon. And what runtime executors try to do is to keep the value n below m in terms of this principle. Also, another problem that might arise is related to mutual exclusion. mutual exclusion is implemented, for example, with mutexes, and it comprises of a critical section, which is a portion of code that accesses shared resources that can be exclusively managed by just one thread. And yeah, we've spoken about some of those synchronization mechanisms which are used to implement mutual exclusion. Yeah, examples of mutual exclusion are functions, for example, printing functions, or yeah, any IO bound functions, which need to be which need to order requests so that IO is consistent. Yeah, well, we also have, yeah, we can just mention Amdahl's law just for completeness sake, because when planning a concurrent algorithm, we're planning a concurrent program, we need to see beforehand how much improvement in performance we are practically we can get in practice, and if the portion of the program that cannot be parallelized is significant, then we might consider whether it's worth parallelizing the rest, because if it doesn't improve the performance by significant factor, then probably it's not worthwhile even considering it. But in general, it's just on the other hand, in the somehow in inverse, if we see on the benchmarks that the performance of a function that we've parallelized using, say, a rayon has improved, say, 3 times, but we have so many threads which are getting spawned, and we've expected a greater degree of parallelism. From that, and from just referring back to Amdahl's law, we can somehow deduce that probably there is a significant sequential portion of the computation which doesn't get parallelized somehow, and there is something that is going on. And we can find by applying the law in such case, we can probably try to guess where this sequentiality lies. Yeah, let's. I'll just proceed with those spooky sides of concurrency. So we have other types of issues such as shared resource exhaustion, and this is where we also exceeding the maximum network bandwidth, for example. We can next just because we've already talked about this. Next is the issue with sharing too much. So if we use, for example, if we have parallel threads that are accessing different parts of a cache line, and this sounds a little bit specific, but I think it's quite it might turn out to be quite common, where um, uh, the values which are or variables which are accessed by those threads are different, but they appear on the same cache line, which is 64 bytes long. And because this cache line is the minimum amount of memory that can be that hardware fetches to CPUs, it needs to be kept consistent with the main memory and with what other CPUs have in their storage. So if several CPUs use the same cache line and they take values from this cache line, they in a sense it's similar to if they just wrote to the same variable, and this is known as cache line ping ponging, where the CPU so the basically the CPU invalidates invalidates the cache in such a way that it needs to fetch the up-to-date data from the main memory or from higher up in the cache hierarchy, and this triggers extra weight because there is latency involved in those fetches, and it's much easier to keep all the data local in the local cache, which has made a few clock cycles latency, for example, as opposed to a few hundred for the main RAM. So this is where we get one of those valuable tips of what to consider when we don't quite know what's going on. Maybe there is a disparity in benchmarks. They are all like they get completely different timings. So yeah, we come to low-level concurrency, which is an explanation of how those concurrency primitives are implemented in the standard library, and it for this sake we also have a explanation of memory ordering models which are implemented in hardware. And those models include special atomic types. Those types are maximum. They are, I think, the maximum eight bytes long, and this is how much we're expected to share between different CPUs in atomic way. There are, as we've seen in this example of two threads incrementing a shared value by one, we have two types of memory operations, which are loads and stores, so reads and writes, just different name, and they operate on up to 8 bytes. So each load cannot take more than 8 bytes in any case. And the compiler will make use of the CPU registers for speeding up access to those variables, and the CPU will pipeline operations in such a way that um, that will make them execute in parallel as long as their execution is completely independent of each other. And also, yeah, the CPU will reorder. In addition to pipelining, it will reorder those memory operations to optimize to apply the common heuristics for um, um, yeah to minimize the say latency when the memory is required. And this reordering is the cause of possible inconsistencies if we don't handle them correctly. So those are atomic types. So as you would expect, they are yeah small values such as usize, booleans, pointers. Pointers are also of type of the same size as usize. Memory ordering has the same semantics as in C++ 2020 standard, and it's discussed in that standard at length. So Jon doesn't. He summarizes it basically, but for further information, we can just go to C++ reference. I will, yeah, I will probably just discuss relaxed ordering, and I might just skip other types of orderings if you have some questions. It's just basically an example of how to use orderings. So if we want an atomic variable, we can decide which type it needs to have, and then we give the variable to a thread by means of arg, or if it's a static variable, then we can just use that static variable. And when we need to read or write, we specify which order is needed, which order we want. And interestingly enough, and I've confirmed that in tests, in this specific example, the value of the function can vary depending on what processor thinks at this exact moment. And in some cases, it might apply the heuristic that says that if the store doesn't depend on the previous load, then it might get executed beforehand. So it just reorders this store before. So it reorders 4 before 3. And so y becomes true. And in the first thread, a becomes true as well. And then x becomes true. And so we get both values equal to true, whereas there is a different case where those operations get executed one after another in the way they appear in the program, and this thread still gets y equal to false, and here x will be false. So the possible values of this function are false, true, and true, true. And this is an example of a problem that might be associated with the use of those orderings. And fun fact, on x86, we don't need those. We don't need to worry about relaxed ordering or whether it provides any speed ups, because on Intel and on AMD, the ordering which is implemented in hardware is is stronger. So it's actually the next level of memory ordering, next strength, called acquire release ordering. And yeah, if we use acquire release, we can fix the example that we've just seen, but it also comes with some downsides. Yeah, I'll just skip this example. It's essentially the same. There might be some reordering associated with acquire release. And if we are, the rule is basically, if in doubt, just use sequentially consistent ordering, or sec CST. And this will be the strongest ordering there is, and it will ensure that we don't have any reorderings of this sort. Next on the list in a low-level concurrent primitives are compare and exchange primitives, and this is something that gets used when we need to implement a mutex, for example, or yeah, if we need to compare and update a shared variable at the same time. So this provides the notion of atomicity in those types of operations. So yeah, we can't implement a lock using acquire release because it doesn't quite get us the atomicity of load, apply, and store. And this is where no, sorry, no, it's just load and update, and not store. Yeah, store is the is still separate. Yeah, but this gets quite low level. So in a sense, after reading this chapter, you will be able to maybe implement locking primitives for an embedded platform, or if you're maybe writing a distributed algorithm, then you will be able to apply the understanding of how to implement locks on a processor to how to implement locks in a in a distributed context, for example. Yeah, the final bit of the low-level concurrency primitives is so-called fetch methods, which can be used to. So if we have an operation which doesn't depend on order, for example, such as +1, it's just a counter, so we don't mind what the initial value of the counter is. We can just apply this function. So this is where those fetch methods are useful. So yeah, hopefully after reading this chapter, you will be able to think a little bit more in depth about concurrent programs and to have more confidence in your skills. The chapter is concluded with some tips about how to structure your day when you're writing a concurrent program. So yeah, always the advice is start simple. For Jon, it's to start with the simplest concurrent design. From my perspective, I would probably add just think if you really need concurrency, maybe you don't, and also think in terms of the portions of your algorithm that needs to be made concurrent. It's common to simply approach concurrency as if there were multiple people or multiple agents dedicated to specific tasks, and which is why we have actor model concurrency. It's very conductive to what people think about concurrent algorithms. But yeah, it might come with its trade-offs. The simplest is just a concurrent design that's correct, maintainable, and measurable. It can be, Jon suggests to start with multiple threads without internal concurrency, so just a thread which is internally sequential, and to organize communication via channels, and obviously use an established library for managing the execution of parallel tasks and for managing communication channels, and to use benchmarks to guide code optimizations. In benchmarks, we can use crates such as criterion and flame graph. Criterion is handy when you need to see by how much for example, your code change contributed to a speed up, or maybe the other way around. If it made your code run slower, then you will see by how much it did. And then flame graph is a library which outputs visual representations of time, essentially, which is spent in specific parts of the program. The next advice is to write stress tests, which are supposed to find some esoteric bugs. And try to in stress test try to go for edge cases, which might be quite difficult. Just to think about what as a person who wrote a program, it's difficult to think about edge cases. There are concurrency testing tools that can be quite useful. There is a model checking tool called Loom, which comes from Tokyo, of the Tokyo project, and it eliminates all the guessing that we need to do when we think about memory reorderings, and it will try to go through all possible permutations of loads and stores. It's still in development, but this is an example of how it can be used. The one remark is that in order to use it, you need to actually use types that are that are provided by Loom itself and not by not the original ones. So it's not the original atomic size; it's the one uh, uh, the one that's defined in Loom, and this is basically because it comes with some sort of annotations. Another tool is a thread sanitizer. It's also part of the. It's actually part of the. I think it's part of the compiler because um, you can simply run the compiler um, with those Rust flags, and the compiler will in effect compile the standard library with your program, and it will inject some dedicated code to uh, in order to monitor memory operations and detect race conditions. Finally, we have an interesting class of bugs which are specific to distributed systems and to concurrent programs, which are called Kaizen bugs. This is a bug which seems to disappear or changes behavior when we attempt to study or debug it. And interestingly, the most common case is the use of print statements because they rely on the same mutex in the standard library, and this mutex in effect synchronizes threads which may not have been synchronized otherwise. And if we remove, so the results will be different with the print statements and without the print statements. And yes, here are the solutions for basically the solutions for say replacements for println logging. So instead of the so-called caveman debugging practices that is using println, there are, as we've discussed, sanitizers, then model checkers, debuggers, which actually can lead you to finding that there is this mutex in the standard library. And also a simple solution is a per thread in memory log, which is only printed at the very end of the execution, and that eliminates any crosstalk or interdependencies. And also using with a framework like tracing, which comes from Tokyo. So yeah, this is the chapter. So in summary, when writing a concurrent program, we need to think about what concurrency model we choose. Also, we need to think how the work how the tasks are going to be synchronized. We need to think how um, how the communication is going to be implemented. We need to avoid deadlocks. We need to take measures in order to ensure scalability. And as for performance, we need to remember Amdahl's law and the limitations. It tells about we need to think about how errors are going to be handled in those concurrent threads, because threads may panic, and this doesn't stop the entire program. So we need to think if we actually need to respond to some errors. and how to how to implement error handling in general. And um, concurrency adds complexity when it comes to debugging and testing, and we've discussed a few tools that uh, can be used in order to make this easier or accessible. And finally, uh, it's good to think about high-level abstractions such as actor actor model and design patterns, which which will which will make your program hopefully more maintainable and more readable. So yeah, this is it. Do you have any questions?
Excellent talk, Vlad. That was brilliant. There's a lot in there. That's a yeah, it's a big chapter. You did a great job on it. For questions, feel free to like unmute yourself or just drop them in the chat, whatever you prefer. You explained everything too clearly. No questions. Um, I dropped it in the chat, but just to mention for the memory ordering, obviously, you did a great job explaining it there, and um, if yeah, it's a topic that people often get hung up on and get a bit stuck on. So I did drop a link in the chat about Mara Boss's Atomics and Locks, which we did a book club on before, but it's all available online. I think her explanation of memory ordering, I think, is a really good one out there. Um, and yeah, but if you have a single atomic, you you can use relax. That's totally fine. Yeah, memory ordering only becomes relevant when you're looking at synchronizing things, and not necessarily just two atomics, but even like other types of data as well. Um, so just be aware. Someone's put in the chat. Do we know who coined the term cache line ping ponging? Any speedy Googlers out
Wikipedia.
there?
Wikipedia. There are a few terms, but yeah, someone in IBM or I'm not sure, Intel.
Uh, but one question in the chat just regarding crates. So how do you surf crates and use the right one for concurrency or any other task? I can mention one thing on this topic, which is blessed.rs is one thing people like to use. I'll drop that in the chat. It shows kind of some of the bigger kind of classic crates, because knowing like which ones are classic, you really know if you're kind of going to talks and seeing what other people are using. But there are certain crates that are like the standard currently, and that can change and it's very opinionated. But yeah, it's useful when you're starting out, definitely.
Even though ChatGPT is uh, like 9 months old, probably the cutoff date for the latest one is autumn uh, last year. It's also useful. It you can just ask for different alternatives. So so that you don't end up on some crate that you don't that no one actually uses. And when you are choosing a crate, go to crates.io and just compare. If you have different crates in mind, just compare the download statistics, and look at the release date. If it's too far in the past, then probably it's not maintained, and it will be a pain um, to compile against other crates. So And because of course with say so I had an example with single seamed example basically, and I still have it in the companion code, but it took quite a bit of time to navigate the recent change in the interface, which happened just I don't know, maybe a few months ago. So I just didn't expect it, and uh, yeah, there was there used to be a crate called fact seamed, which implemented single instruction multiple data on types like, for example, something that you can pack in a word. So you can say have eight um, 32-bit floats in the same word, and then you can apply in an operation to all of to all of them. And there used to be a separate crate, but now it's in the standard library. But it needs a nightly feature, and when you, I'm not sure what happens if you don't want this, if you want to stay on stable. I think you just need to use an old version of Rust, because in recent versions of Rust the old seamed crate doesn't work. So it doesn't. It still needs some functionality which is no longer there. Yeah, and that depend on hardware, and that that also that are also in heavy development. For example, hardware locality crate, HW locality, which allows you uh, to make use of the non-uniform, like the topology in a modern processor is highly non-trivial. So that like memories can get attached to one side of the die, so it will be closer to some processors, and some other process will be far away. And to make use of this irregularity, there is a crate called HW locality, which actually is just an interface to a C library, a HW loc. Um, and it's if you try um, in the problem is that the interface changes very quickly in this library, and it has been recently stabilized. So it's now in version 1 alpha something. Yeah, it's version 1. Mhm. So you might get um, a little bit of a kickback uh, from unstable interfaces.